Hi everyone, welcome to the February edition of the Live and Know Data Science Seminar Series. Today we're joined from the University of Rome by Simone Scardapane, who's going to be talking about AI and scientific discovery, a retrospective. So if you're ready, then please feel free to get started.
Yeah, I'm ready. Okay, so the seminar is roughly 40 minutes, right? If I remember correctly, then we have some time for the Q&A. You can hear me correctly, right? Before I start?
Yeah, all good.
Okay, so just as a way of presentation, I'm currently a tenure-track professor here in Sapienza, and I'm also involved in we'll see a little bit in our nuclear physics institutes, which is why I'm collaborating with the University of Liverpool, and I'm joining here. And I'm recently also involved in our advanced School of Advanced Studies, where we're doing a few additional studies. I'm quite active on Twitter if you want, and I also recently published a book on building neural networks. Now, the reason I started doing this talk a little bit around is that this idea of AI for science discovery is massive recently. If you look online, there's a number of position papers, survey paper retrospectives, of for example, this a couple of years. And everybody can see the impact. I work in Sapienza. One nice thing about Sapienza is that we basically have every possible field of study you can think of, and every field is impacted. So I get calls with archaeologists, paleographers, geologists, physicists, jurists. I mean, it doesn't really matter what you're working on. At some point, people will start saying, okay, look, we can apply AI here, okay? And I like this survey both because it's a nice indication of the fact that it has, it was growing already, but it had sort of undergone this massive boom recently. And also the sentence here, oil and water, because we'll see it's not really a nice, perfect combination, trivial combination. And you also find this kind of gigantic talk. Terence Tao is one of the most notable mathematician, and it's a lot of time that is doing these interviews where he says that thanks to large language models, for example, we are now entering this kind of new math where the combination of the mathematician and the LLM can bring about, a sort of complete revolution for mathematics, and we'll talk a little bit about this. So I started doing the talk, and I realized I actually had a lot to say because when you have this very stupid view where you have the scientists and the discovery on the right, and you have this artificial intelligence cloud in the middle. One big issue that I have is that the idea itself of what it means to do artificial intelligence has changed basically every year. So if you ask someone 10 years ago, someone who says I'm doing artificial intelligence, he would have told you that he was, I don't know, training his own systems, doing his own systems. Then everybody switched to LLMs, to agentic now LLMs. I mean, basically every year there is a new discovery, a sort of new buzzword. And of course, this impacts the scientific field because the way, if you change the way that artificial intelligence works, if you want, it also change what it can do for scientific discovery. So the idea of the talk is that we make a very brief retrospective where basically I pinpoint a few key points in what has happened in artificial intelligence recently, and also how this has changed the way that AI is used for science. Okay, and I would like to give you three. I'm not really sure about the background here, so how much what I will say is, I hope not too trivial, but I'd like to give you three key points. And the first one is that the main topic, let's say, that we see in the last years is scaling. So what has changed dramatically over the last 10 years is not an algorithmic change, it's not let's say, a fundamental view change, but it's simply the fact that we are able to scale, we scale these models at an absurd level. And we realize that by scaling them, the performance tend to increase. This has become known as the scaling laws. And this is interesting because it means from let's say, the scientific point of view that at some point these levels will reach a sort of accuracy that is comparable to what I called here PhD level. So a few years ago they were struggling just with I don't know, writing coherent text, and now we're talking about whether they can do Olympiad level math, for example. So of course there is an interest from science because it means that at some point the performance gets such that they can solve the same tasks that a scientist could solve. And then the opposite is that if you assume that a model can solve a task, you also have to assume that the knowledge about how it must be solved has to somehow be embedded inside the model, and you'd like to extract it. So the second big topic is that of explainability. So trying to open the black box of this model and understanding what they're doing. And the third one is also that I'd like to discuss a little bit how the interface has changed. So the way that, I mean, if you are a scientist and you are interested in using artificial intelligence, the way you work with these models has changed a lot. And also it will change. So I'd like also to say a little bit about the future of these 3 points, if you want. Of course, I can see the screen, I cannot see the participant, but if you have questions in the middle of the talk, feel free to stop me and we can discuss them instead of having all the questions at the end. So again, the talk is structured as we'll see a series of what I believe to be very interesting points, okay? And at that moment in time, how was let's say, the relation, if you want, between the AI scientist, AI expert and the scientist, okay? And if you look at artificial intelligence, maybe I guess you know that, depending, but the big defining moment, the first big defining moment comes around 2012 in what has become known as the ImageNet moment, in quotes. Because if you look at the technology that we are talking about, every time we discuss artificial intelligence, beneath it, there is something called an artificial neural network. And the point is that an artificial neural network is not really a very complex piece of technology. It's basically a very big mathematical formula that is here. I wrote efficient and differentiable. Differentiable means that it can be optimized numerically given a certain set of data. We'll see that. And it's a very efficient tool when you're working with complex data. Okay, so every time you have a problem that involves image, text, audio, graphs, all these kind of, let's say, very structured and sophisticated data, and a neural network is probably a good thing because it allows you to process this data in a sort of numerical fashion that can be optimized. And the key point is that inside this neural network, it's basically a very big formula. And inside this formula, there are a number of parameters. These are numbers that define the behavior of the model. So depending on how you specify these numbers, you can change the way the model works. And this is what a scale, if you want. So now we're talking about models that have billions or tens of billions or hundreds of billions of these numbers. And so if I tell you these numbers, you know exactly how the neural network works, basically. So the task is finding the specific configuration that solves a certain task. And let me talk a little bit about, so imagine that it's 2012. If you were projected back in time to 2012, the way that this model worked was that you identify a certain task. So maybe you are a scientist that is working on finding new proteins that have a certain characteristics. Or here it's a problem where maybe I want to transcribe a certain audio file. So what you do is basically you collect examples of examples of the task you are trying to solve. Okay, so maybe you collect, and these are so-called labeled examples. Okay, so for example, if you're trying to understand whether a certain molecule is chemically reactive to something, you need to find a bunch of molecules and then manually say, okay, this one is reactive, this one is not reactive, this one is reactive, and so on. And in practice, this was the big bottleneck, because doing this collection is a very time-consuming task, especially in science, where you need a lot of domain expertise, data might be limited, etc. First, which is how many examples you were able to collect. Is connection able, otherwise service. Hello?
Yeah, I think your connection is a little bit unstable. You keep just cutting out for a brief second.
If you give me, if you want to give me just 1 minute, I can change computer and it might be better, because I have another computer with a fixed connection.
Yeah, if you think it'll just take a minute or two, then yeah, that would be good.
Okay, just wait 1 second. Okay, I think this one is much better, right?
Yep, that's good.
Guys, so let me go back here. So let's say that this was, let's say, the major bottleneck, okay, because that was very time consuming. Now, once you had these examples, what you did was to define your neural network. And I mean, I won't go here, but this was a sort of simple process, because depending on the type of data you had, you had a certain design of the network, and you kind of randomly initialize the numbers inside. So here you have a second dimension, and the second dimension is how many parameters you have, and the two are correlated. Okay, so if you had a small number of examples, you had a very small network. If you had a very big number of examples, you had a very big neural network. Then you throw this inside some optimization routine, and again, this is practically automated. But it has another important dimension, and this dimension is basically, if you have a lot of examples, you will have a big neural network, so you need a lot of computing power to optimize it. And today, computing power, we'll see that, but it's basically defined in terms of how many GPUs, graphic cards, you are able to get, okay? So these three factors go together. So if you have a very little number of examples, you need a very small model, and so you need a very little amount of compute. And then this spit out the final neural network, which means that it finds a certain configuration of the parameter such that the task is kind of solved if you have enough. And so you can use this neural network. And that was a sort of very simple, elegant process, and you can change it a little bit, because you can, instead of starting completely from scratch, you can start from a neural network that has already been trained on some task that is kind of similar, and this is called fine-tuning. The point is that this is not a very novel idea. So for example, if you go back in time to the 1989, there were already some neural networks in production that were doing exactly this. Okay, for example, this one is a very famous example about digit recognition for checks, also for the post office. And it was practically identical to what you would have done in 2012. So you have the input, this is the design of the neural network, which is a specific design for images, let's say. Inside you have a bunch of parameters, and you train it with gradient-based learning, which is basically what we do today. Okay, so what is the difference is that this is a very small task for today's standard. So the images were small, the number of images were really small. So as a result, the networks were also pretty small. So at some point, people said, okay, but I realized that the big bottleneck that I really believe that neural network can do better. So, and the big bottleneck is the amount of data that I have. So what they did was to collect a lot of data. And what is a lot of data is basically so 1 million more images that were manually annotated. And in particular, this has become known as the ImageNet dataset. So it's a dataset of a little bit more than 1 million images, which are labeled manually in 1,000 classes. Okay, so that was sort of a multiple order of magnitude more than what was available at the time, which meant that you could craft, let's say, you could build neural networks that were larger. Which brings to 2012, because what they did was to organize a competition on this data. And before 2012, 2011, almost no one was using neural networks. And then in 2012, a couple of teams decided to participate with a neural network. And they were able to scale it up compared to neural networks that were used at the time. They had to manually connect about a couple of GPUs. Was a very sophisticated software hardware task for the time. But the point is that it's not seen here, but it improved a lot compared to every alternative. So basically, everybody at the competition was running for 1-2 percentage points, and they were able to get dozens of percentage points more in accuracy. So you see from here, from this graph, that what happened was that in a few years, imagine that these points are basically the amount of people that participated in a competition with a neural network. So basically, you don't see it here, but in just a couple of years, for 3-4 years, the entire computer vision field switched to neural networks. Okay, so an entire scientific community decided to do something else. It was really a big revolution. I mean, it's really hard to imagine from the outside, but imagine everyone working in the scientific field was doing a certain number of algorithms and things, and then suddenly in 4 years, they were all doing neural networks. And what happened was that this pushed a lot, basically, the accuracy. So what is happening here is that year by year, now the big bottleneck was not data, because we had a lot of data, but the size of the models. So people find way to build bigger and bigger models, which meant that the accuracy kept increasing, you see, until a certain plateau. And this plateau is basically the best accuracy you can get on this data. So it's really impossible to go beyond this accuracy here. So the task was considered solved. And now everyone, let's say, around the world was interested in neural networks. And this, I mean, let's go back quickly to science. So how do you use at this time these kind of models for science? And the point is that there was a big, the graph is really bad, but there was a kind of decoupling, okay, between the scientists. You needed two figures. One was the scientist and the other one was the expert. Because you see here, even if it's simple, I mean, you still need to like define how to collect this data, build this neural network, do the gradient descent optimization tasks. So I mean, it's a lot of things which, okay, they're not rocket science, but they're not simple, so simple. So you need a little bit of expertise. So what happened was that the scientists identified a problem. It collected the data and it sent that data to the expert. Typically, these are two different figures. So the expert trained the neural network and gave it to the scientists, which that use it as an app, basically. So you see there. And what is the problem here? The problem was that it works. We have a lot of interesting success stories, but it's really indirect, because the only way that scientists here can impact what is going on is through the data, basically. So the only interaction that you have between the expert, it's that I collect more data, I collect less data, I collect better data, and that's it. Okay, so that's a little bit the framework that you had for science a few years ago, with a lot of interesting applications. For example, you had a lot of applications in medicine. Here it's an algorithm about detecting retinopathy, diabetic retinopathy from the cornea, basically. So here again, you ask doctors to label a lot of images of of retinal fundus, and then you train a model with this, and you get very good accuracy with a Nature publication. You have a lot of applications in high energy physics, for example, which is, again, why I collaborated with Liverpool about detecting signal from background in simulations of collisions of particles. And recently there was a lot of buzz because you had a neural network that was able to basically read, transcribe what was written in a papyrus, one scroll that was found at Herculaneum that you couldn't open, basically. So they did a bunch of analysis to digitalize this scroll, and then they were able to unroll the scroll and read it with a neural network. Designing new antibiotics. Here you use the neural network as a kind of filter that gives you interesting molecules that have certain properties. So you see, I mean, I am finding new exoplanets. I mean, I could go on and on and on, but the point is that all these very big success stories has this pipeline. Okay, so the expert, the ML expert gets together with the scientist, they identify the task, they collect the data, they train the model, they put the model into production. So very successful, but also a little bit limited, and limited in at least two major. So if you ever did this, let's say, if you try to do that, you immediately start interacting with the scientists, and you immediately get two major problems that the scientists would like to solve. The first one was that, which leads to what I call here classical explainability. The first one was that the scientist typically has a lot of domain knowledge. So maybe the physicist knows a lot about the way the data is simulated, for example, or about how proteins interact between each other, okay? And you see there is not a lot of, it's really hard in this scenario to push this domain knowledge inside the model, okay? Because again, the only way you can truly control the model is by changing the data, okay? Collecting new data, removing data, relabeling data. You don't really have a way to push directly the domain knowledge into the model. And there were some solutions, maybe some of you know about physics-informed neural networks. Physics-informed neural networks were this idea where if you had knowledge in the form of stochastic differential equations, so differential equations, you could put this knowledge inside the loss function, basically. So force the model to conform to specific physical knowledge. But what's the problem here? The problem is that this is really difficult. So it's difficult in terms of optimization, it's difficult in terms of automatic differentiation, and also it requires someone to be an expert in two things. So you need to have physicists that were also kind of very good in neural networks, which is not really scalable if you want. And also, I mean, there is only a limited amount of things that you could include with a neural network. This is an example that I like. So it's a few days ago. So if you test this, the most best performing GPT models existing on multiplication of 2 digits, I find it funny that even the best model that you have, they struggle in multiplying two numbers once you go beyond a certain size. So if you multiply, I don't know, 20 by 20 digit, you get a 0% accuracy, even in the best models, okay? Which is a bit weird if you think about it, because you say these models are intelligent, and then they fail in this task, but we know how to solve this task because we have, I mean, very simple algorithm that can multiply digits at practically every level of accuracy, and yet even now you don't have a very simple way of injecting this knowledge inside the models themselves. And then the second, problem was that every time I also did a lot of work. I don't know. We did a lot of work designing algorithms that were transcribing manuscripts or stuff like that. You had a very good accuracy, but then the scientists said, okay, I really like this, but why is it so good, right? So if it's able to detect certain type of collisions in the data that I'm showing it. I don't really care about just the output, the prediction. I want to truly know what is happening inside. This is the so-called explainability problem. Okay, so the problem of opening what is happening inside the neural network and understanding the mechanisms. And it was a very big problem also in terms of, in Europe, we have regulations at some point that force people to kind of explain the predictions if they were used in an automated loop, etc. And so there was a lot of push to develop explainability techniques. The problem was that these explainability techniques were very simple. For example, the most common explainability techniques that we had at the time were this kind of saliency maps, basically, where you have a model that has a certain prediction, and you are plotting. Sorry, it's here on the fourth column, a heat map basically that is highlighting the region that the network is using to make that prediction, which is, an interesting data that you want, but it's really, really limited. And also, you should, for example, if you have a medical task and the model is making a diagnosis and you augment this diagnosis with a heat map, again, either the heat map, it's very nice, and so or you're not very confident in the heat map, but they don't really give you a way to control the model based on the result. You cannot tell the model, okay, it's not actually, you shouldn't focus here, but you should focus on another region. So those were kind of very, very limited solutions. Let me skip this one. There were also alternative ways. So instead of, for example, focusing on what input points were the most salient, you could try to find what training points were the most salient. So for example, to find if you have a certain misclassified point, or if you have some memorization. So basically you have a neural network which is given a question, it makes a prediction, and then you find in your training set what are the training points in the data set that are the most relevant. And so there was lots of work. Sorry, let me skip this one. But basically, at some point after a few years, people realized that they were not really good. Let's say, okay, so we had a lot of ways of computing saliency maps, for example. All these methods give you contradictory results. They are kind of not very robust, not very faithful. Basically, they don't work as you expect, and they are also not very useful in controlling the model. So they almost all the results, there was a period around 2018, 2019, where you had a lot of negative results, basically, which led to kind of distrust of this technique. So you had this, for example, this 3 years ago by Zachary Lipton. Zachary Lipton is faculty at CMU. He has worked a lot in medical tasks, and the problem is that basically people were using these explainable AI models to sell these techniques, but then the explainability was really not working as they intended. So it actually created a kind of negative loop, because people put into production this explainable AI model, but they were not really good. So people came to distrust both explainability and artificial intelligence. So he says, the precarious state of interpretable deep learning is that actually we should be more scared for hearing that you deploy an explainable AI technique. Okay, so not very good, not very good also for science. So let me take a step back. So explainability doesn't work a lot as expected, but at the same time, and also we had another issue. So it's 2017, and the other issue was that the performance on ImageNet was sort of reaching a plateau, and so you couldn't scale anymore the models. And the idea that came out around this time, was known actually, but become more interesting, was that one way to scale was to try to find, not label it, datasets, but unlabeled dataset, which means datasets that don't have a very precise label attached to it. So for example, instead of, you do text classification, it's a labeled task because you have a bunch of texts and each text has a classification attached to it. An unlabeled dataset, it's just a dataset of text, random text. And why is it good? Because when I say we scale the data, I mean orders of magnitude. So if you have a million size labeled dataset, the next scale up would be 10 million images. But labeling 10 million images, it's really difficult. By contrast, finding 10 million images might be easier randomly around. And similarly for text. I mean, we didn't have an ImageNet-like dataset for text, but we could easily find a lot of text. And so the idea was, then it became popular as this foundation modeling idea. So basically, you take this gigantic dataset of unlabeled task data, and you basically, what do you do with this unlabeled data? You find a kind of proxy task, some random task that you can build on this data, on which you can optimize this a model, basically, that is known as a foundation model. And the point is that this foundation model is actually useless by itself because it's optimized on some auxiliary task on this unlabeled data. But then you can take it and fine-tune it, optimize it for another task to find new models. And the point is that if this data set is ginormous, this foundation model is really big, really good. So maybe the fine-tuning will require only a very limited amount of data. Which, I mean, see, you can, using this idea, you can really scale up. Because, for example, you see, in terms of text here, you can quickly go from datasets that are around gigabytes to datasets that are around terabytes. Today, we have datasets that are in the order of petabytes, and the same is true for images. Okay, so once you ignore the fact that these images have to have tags, you're free to go around and basically gather every possible image text that you can think of. Text is a particularly interesting, scenario because you have ebooks, you have GitHub code, you have, I don't know, forums, Reddit. I mean, practically everything that you can think of is written in text, and you can just throw it inside the model. To the point, just a curiosity, that we assume, for example, that we were able to basically exhaust high quality text. Okay, we don't know what other sources of high quality text we could find at this point in time. Of course, what's the problem? The problem is that you collect a petabyte of text, but then you need to decide what to do. Okay, you need to train this model, foundation model, so you need this kind of auxiliary task. And there were a lot of proposals for computer vision, blah, 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 but the most important proposal, sorry, pieces here in Italian, was proposed by, not popularized, let's say, but what is today very known as GPT. GPT stands for Generative Pre-training Transformer. And the key point is this pre-training, the P, because as I told you, this is pre-training. So it's like we wanted to build a gigantic model for some downstream task. The key observation was simple. So you have a text. We won't go in the details here, but in order to process it with a neural network, you perform an operation that is called tokenization. Tokenization means that you are basically splitting this text into discrete components, which are known as tokens. And the fact that they're discrete is very important because a very simple task that you can train for your neural network for is predicting the next token. So basically, you can take any piece of text here, look at this foundation, no? And you can train the model to predict the next token, which is very simple because you have that token in your text. So you can just mask it and recover it here. So the model will give you a distribution over all possible tokens, and the highest one is the next one, basically. So, and this is a very interesting thing because once you do that, you can take this token, throw it inside, and continue generating, basically. And this is this was a generative pre-training model transformer in 2018. And again, I think that the P is very interesting because pre-training means that we don't really care about that, because we care that it's really big, because then we want to use it for something else. And then in 2020, now it's a bit, everybody has interacted with GPT, but the ChatGPT, for example, Claude. But the idea came just a few years ago. And what was the idea? The idea was that if you have enough data, so you are able to train a model that is sufficiently big, instead of doing fine-tuning, so which is the right here. So you see, you want to translate things, so you fine-tune the model for translation. So you need to collect translation data, you need to do gradient, to fine-tuning, optimization, etc. You could just ask the model directly to solve a task. This is what is called here zero shot. So you could actually ask the model, please translate this sentence from English to French, cheese, and the answer was fromage. And the realization was that after a certain level of scale, this was possible, and it was not possible before. So it meant that you could take this big, gigantic model and use it immediately to solve a certain number of tasks. And this has changed radically the way you interact with the models. For example, a lot of time I try this example where basically I take all the experiments, all the works that we did using, let's say, fine tuning. Here it's, for example, a transcription of some handwritten manuscript. Okay, and so what we did in the past was that you had to collect a lot of data, ask a paleographer to manually transcribe it, train a neural network for transcription. But then here I can just open up ChatGPT. This is a few days ago. I throw the manuscript inside and I just say, okay, can you transcribe this text? And this is the Divina Commedia. It's a 15th century handwritten manuscript, and the answer is actually really good. Not perfect. Example here, it's broken, but kind of really good. So you see here, what I find interesting and maybe not yet truly understood is that even for science, the barrier for a scientist interacting with a model has decreased dramatically, because now you don't need to start. You don't need to collect data, train the model, blah blah blah. You can just try one of the existing models, and maybe you have a small benchmarking data set to see how it works. And maybe it works. Maybe you need to do some fine tuning, but maybe you have a task where it actually works pretty well. It has a little bit also of explainability, because, for example, here, you see I can a little bit control what is happening by giving some domain information, for example, the century, where the manuscript is coming from, but also I can ask if I ask, can you classify this picture? But then I ask, can you explain? And, and I get a kind of textual explanation. It's not perfect because it can hallucinate, it can give me very weird results. But it's interesting because suddenly, I'm kind of completely revolutionizing the way I'm interacting with the model. So that's 2018, 2019, 2020. And so at this point, the only interest was scaling, because these results of the GPT-3 result was telling you was that the only thing that really mattered was the scale of the data, the scale of the models. Every time if you scale enough, you basically unlock new capabilities, which was formalized at some point under this idea of a scaling law. So you see, since 2012, all the dimensions have grown exponentially. Formalization of the scaling laws. What is a scaling law? Let me give you an example. The scaling law means that if you plot the three elements that I discussed, so the data size, the parameters, and the amount of compute, you throw these three, again, are correlated. Okay, so if you increase one, you need to increase also the other. If you plot the loss, so here it's a next token prediction loss, you see this loss kind of follows okay, you can fit a line basically, okay? And this is a scaling law. So it means that by fitting this line, you see these coefficients here, you can predict what happens when you're scaling. Okay, so for example, if you are here, in this point here, if you can see the cursor, I have a certain loss, but because you have this linear trend, I know that if I multiply by 10 all my parameters, so if I gather 10 times more data, if I invest 10 times more compute, I can predict that I have a decrease in loss up to this point. And this is an empirical observation, but it's really important because what is happening is that at this level of scale, things are getting very expensive. Okay, so if you want to go from here to here, maybe you need 1,000 euros, then you need 10,000 euros, then you need 100,000, then you need $1 million. Okay, and when you start needing millions of dollars for training, you need to be very, 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 very confident that what you do will give you something. Okay, will get you an improvement. And if people had not formalized this idea of a scaling laws, you would not have had this confidence. So before the scaling laws, very few number of people were truly confident about this. And when people started seeing these results, they were starting to be very confident, actually. This is a blog post by Sam Altman, who's the CEO, of OpenAI, and he wrote a little bit here about, blah, blah, blah. We may have super intelligence in a few thousand days, a bit excessive if you ask me, but how did we get here? And I find it interesting here in 15 words, neural network worked. And the worked means that they got predictably better with scale. And we dedicated increasing resources to it, which is kind of the key. So at some point we realized nothing really matters. I mean, only the scale matter. So the only thing we need to do is throw a gigantic amount of money in compute, data, and the size of the models. And you can see it here. It's a very interesting graph from last year because here you can find the compute on the x-axis, which is in flops. But the most important thing on the y-axis is how much money training these models cost. And you see, we are getting to the billion. This is 2024. Now we are in the billion range. So if you want to train a model, you need hundreds of millions of dollars, basically. And we saw this increase. So we had a period here where everybody was releasing its own large language models. So you had GPT, Gemini, Llama, and then people were able to also scale it up by adding image data. So you get this vision language model like GPT-4, Gemini Ultra, and now we have even more complex models where, for example, you have audio. Why is scaling interesting also from a scientific point of view? This is a very rough idea, okay, not a formal idea. But the point is that, the fact that this gets better and better and better is not a trivial thing because at the scale we are right now, every simple task that you can think of has been solved. So for example, we call these objects language models because the task 10 years ago was to generate text that was actually grammatically correct, semantically correct. But this is solved. So if you will almost never find a grammatical error again in ChatGPT. So it means that you cannot improve by learning to write better, for example. And basically, every task that is kind of simple is already being solved pretty well. So the only way in which this loss can keep decreasing and decreasing and decreasing is that if the model gets better and better, are tasks that it was not able to solve previously. And this has become known as emergent capability. It's a bit of bad term, but the point is that every time you scale up the model, you see improved performance on tasks that were unsolvable before. So there is a scale at which you learn to make very well arithmetic. There is a scale at which you see very strong improvement in multi-step reasoning and so on. So here you have 137 emergent ability. The point is that once the model learns to solve a task, it very quickly gets to a very, very good accuracy. So the only at the next level of scale, it will get better at other tasks, more complex tasks, you see? And I really like this example here. This is a couple of years ago. It's a video generation model by OpenAI. And you see when you are dedicating a small number of resources, the model is good, but I mean not very good. You know, but then as you increase the compute, so you see 4 times, 16 times, the results get really better. And the point is that if you look at the image here, you see you have a very good photorealistic image. So so it's like a language model. So you start from sentences that are kind of incoherent, but then you get to a point where the sentences themselves are really good. So now if I happen to increase the compute 4 times more, what would happen? How can it improve if you want? And for example, today people are asking themselves that maybe, I mean, the way the video generation models can improve is by kind of embedding a kind of principled model of the physical world. So trying to understand basically becoming better and better at handling, I don't know, gravity, at handling collision, at handling the fluids, and so on. So you see here, two generative video models learn physical principles, which is really interesting because it means that at some level of scale, this tool become immediately useful as video generator, but also physical generator, game engine, and so on. Which is why now there is an interest at scaling up all sorts of models. You know, people are designing gigantic protein language models because they realize that, again, they hope that the scaling law will keep holding. So, you know, as you scale and scale and scale and scale, the models get better and better and better, and they are able to solve more and more and more complex tasks. So not just generating simple proteins, but designing proteins with any kind of complexity, basically. High energy physics foundation models, basically models in every possible field. Okay. Which brings me to the last topic that I wanted to discuss. So you see, the scale is really interesting because it gives you these models that are generalist, very powerful. Every time you make one step in scale, you get new capabilities, basically. But still, you would like to answer this question on where, I mean, how is the knowledge, for example, about these tasks encoded inside the models themselves? Because you see, you can do this kind of visualizations where you kind of see that, you know, this is a convolutional neural network, if anybody has used it. This is a visualization of the activation maps, a visualization of the filters. And there is this idea that there is somewhere, let's say, localized knowledge about what is happening. And you'd like to extract it because, you know, if you're solving a protein generation task, you'd like to truly understand how this protein was created, not just treat everything as a black box. So you see, you have this idea that if you look inside the model, ideally you can find here localized behavior that combine to create higher level behavior, and you can basically retro-engineer the entire model and truly understand the individual components that compose the complete answer. And a few years ago, there were a group of researchers that were at OpenAI at the time that published basically a manifesto, you know, claiming that this could indeed be done. So that, you know, you could find what they called interpretable features. So pieces of the model that corresponded to things that I could understand, and that these components would connect in ways that they call circuits that, again, can be studied and understood. So they claim that you could take a very big neural network and you just like you take, you know, this bad, let's say, metaphor, but you take the brain and you try to investigate every single neuron, every single functional area inside the brain to try to understand what it's doing. You could ideally do the same here, which is really interesting, you know, because again, for large language model, but for science, it means that every big model that you train for a gigantic scientific task, then all the knowledge about that scientific task is somewhere inside that model, and you just need to extract it. They did a lot of experiments. Let me skip this one. The big issue that they had was that basically neural network act by manipulating vectors, so blocks of numbers in very high dimensional spaces. And the way that the information is encoded inside the neural network, it's very dense, very distributed, not very interpretable, if you want. So a very popular idea today, for example, is that you can basically train a kind of mappings. These are become known. These are known as sparse autoencoders, which basically translate between the original activations of the models to a space, a very extremely high dimensional space where each element is highly interpretable. These are called sparse autoencoding. So what is the idea? That you see, these are the tokens, so these are the text token, and they go through the model. And at every point in this model, they are represented by this vector of, I don't know, here, 512 numbers. And you translate this to a vector of here, 100,000 numbers, each of which represent something that could potentially be interpreted. The issue is, again, one of scale, in the sense that now you need to find a way to manually interpret these components. And the way you can do that is by basically automating it with a GPT model. Because now GPT works so well, I mean, Claude, any model, Gemini, that you can automate. So the idea is that, for example, you take one point in the model and you show the activations to GPT, and you ask, can you give me an explanation? And here, for example, the model is telling me, maybe it's looking at movies, characters, and entertainment. And I'm sorry, I skipped it here, but basically you can then test this. Let me open it quickly. Wait, here, see? You can basically test it quickly by basically asking again the model to, okay, you told me that this neuron is activating in response to this sentence. Can you now predict the kind of activation that I will see? And you can score them according to the real activation to see if the prediction was good. So this is called as automated explainability. And the interesting thing is that it seems, sorry, it seems to work in the sense that at some point, Anthropic, which is now, I mean, very known company that releasing the Claude series of models, published a few blog posts where it says that, look, I'm able to extract millions of these interpretable features. For example, let me go here. This is a very famous example. They found a feature that was activating on the Golden Gate Bridge. So there is a piece of the neural network that will always activate every time you reference the Golden Gate Bridge, for example. And there are, if you go here, let me skip this, scaling low, blah, blah. You see there are features that activate every time you're talking about brain science, features that activate every time you're talking about popular tourist infrastructure. There are, let me go here, features that activate every time you have, where is it? Wait, what is the interesting thing is that, why are you interested in that? Because if you know, for example, where everything connected to the Golden Gate bridges, okay, you can control a little bit the model by basically modifying this feature. So for example, you can always activate it as much as possible. And you see that now it will always answer in a way that involves the Golden Gate Bridge. But this is true for everything. So you see here, they found a feature that activates every time there is a bug in the code that you are generating. or that you are reading. And if you remove this feature, the model becomes unable to actually find bugs, for example. So it's a really interesting thing because you are finding interpretable thing, and you're also learning to control the model by modifying these interpretable things. And you can do that for science, and this is very, very recent. A few days ago, they published this Evo2 model, for example, which is a protein, a model trained on very long sequences of amino acid, and you can replicate this entire thing to find a lot of interpretable things. Interpretable from the point of view of biology, so features that activate based on coding sequences, protein secondary structure, reactivity, and so on. And you can check, okay, you can check whether these features make sense from a biological point of view. And just to give you an example, I find them interesting because they may change in the future the way we interact ourselves with the model, because they can give us a way to control them. So here, for example, this is a Llama 3 model. See, maybe I can ask a physical question: how many quarks are there? And the models is running here, and they would answer me that there are 6 types of quarks. But the point is that this is how you would interact typically with the model. But then maybe I can say, I can highlight down here, and the model will search for what kind of interpretable features are being activated in the model. And you see here, there are a lot of tokens that appears to be, a lot of features that appear to be physical. So there appears to be features that are related to every time we mention quarks, strong or common, keywords related to concepts and method in particle physics, mentions of spin, etc., etc. So there are already a lot of interesting physics things. And you can try to steer the model here. So what you can say is that, okay, it won't probably change anything here, but take any neuron that knows about particle physics, see, and suppress it. So basically remove everything that knows anything about particle physics, and
imagine after you've had a bike accident,
it will regenerate now nothing is truly changing here because but you could ideally change and control the model in the future by acting in this set of interpretable features. And it's not perfect. There has been a lot of papers now that are discussing limitations of this model. So very quickly, I'll go through some future, let's say, idea. One is that you may have found a lot of interest in these reasoning models. What are reasoning models? Are models that basically, instead of directly giving you the answer, they have an intermediate step where they produce a lot of tokens that are not directly used for the answer. And these are called the reasoning tokens. And so you have DeepSeek, for example, and these are interesting because you see scaling laws also for the inference now. So instead of pushing money into the training part, you push money into the inference because you can generate a lot more tokens, reasoning tokens, and the accuracy sort of improves. Again, I don't think it kind of changed a little bit the task. Why? Because the way these are trained is by finding tasks that are really, really difficult to solve. And basically what we have right now are either coding tasks and math tasks. So these models are expected to be very, very good at scientific tasks where you can verify the answer, basically. And they're also interesting because while we are seeing a little bit of upper bounding in the standard scaling laws, we seem to see no upper bound for now in this scaling stuff. Well, there is a little bit of a agentic model. I skip this because we don't have a lot of time. I'd like to mention that actually the big problem is that we're seeing a bigger and bigger gap in what we can do as an academia because we don't have the money anymore to compete with this kind of model, and this gap is growing larger and larger. It's an interesting, let's say, topic of discussion with not a lot of solution, because these big models are becoming really, the training of this big model is now the province of a very few actors. And what I'd like to also point out is that given the scaling laws, you should never trust any benchmark, let's say, because every benchmark, irrespective of its content, at some point will saturate. So you will have all these benchmark where the model is not working, and then at some point it will saturate, and the people will tell you that the benchmark was solved. So for example, this was this very big benchmark called Humanities Last Exam, where they collected a lot of very, very difficult problems like this one. You see, provide a translation from this script. Initially, the models were very, very poor, like 3%, 4%, and now we are around 22, 25% already. So, and I guess it will get larger and larger. So a single benchmark, let's say, will never be a test of general intelligence, because any benchmark at some point, because of a scaling law, will simply saturate immediately. And there are also interesting things, because, for example, the same models that can do this may struggle on simple benchmark. So this is a benchmark that was published a couple of weeks ago about reading clocks and reading calendars. And lots of models are having a lot of difficulties on this benchmark. So it's kind of funny, because you can saturate a benchmark and yet be poor on other benchmarks that seem simpler. A very interesting direction, I like to give you this because it's the most interesting direction, I think, is that we are trying a lot to implement, push, let's say, this idea about interpretability back into the models. So instead of having models that then you interpret, you would like to have models that are already interpretable. And for example, this is a paper from, again, last week, which showed that you could add a kind of sparse autoencoder here in the middle of the neural network. If you train it on a series of tasks of predicting the dynamics of galaxy evolution, you get some interpretable features, basically, already by default, let's say, which is a very, very promising direction in general for science. Okay, that's it. That's a very long, high-level overview of a lot of things that have happened in AI over the last 15 years. Thank you.
Oh, thanks so much.
Sorry, I haven't seen the chat. Links, yeah, you wait, I can immediately give you the link, actually, because yeah.
Great, thanks very much. Okay, so as usual, we'll take some questions from the room if there are any. And anybody online who would like to ask a question, either raise your hand or drop a message into the chat. So, see, Joe's very keen.
Yeah. So DeepSeek has been in the news for apparently reducing the amount of compute needed for similar results to ChatGPT. Does that change the outlook of non-academic actors being able to outpace us always, or is that not so relevant?
Yeah, it's a good question, but I don't think it changes the so much, in the sense that when DeepSeek came out, first of all, the results were in line with the model that OpenAI had in production since a few months. And now OpenAI came out with new models that are better than DeepSeek. So let's say that there is, in my opinion, one order of magnitude gap always in terms of money between the open source and the closed source. So it doesn't significant. So and even the closed source already requires, even DeepSeek require millions of dollars of investments at least, you know. So no, I don't think it changes that much. You have a gap. The gap is still there. I have a picture. I forgot to add it, but a gap between the open source and the closed source, and even the open source and this gap is order of magnitude. So maybe now you need millions of dollars if you want to be the strongest open source, and you need tens of millions of dollars if you want to be, or hundreds of millions of dollars, like Grok, OpenAI, let's call it XI, if you want to be the top closed source. So it's every year the gap remains, but it grows. The two lines grow, so the amount of money grows also.
Any other questions in the room? Yeah, Andrea.
Yeah, thank you very much for the nice overview of the last 15 years of research in AI. I was very interested when you start talking about this sparse autoencoder for interpretability, but I think I didn't really understand it. So you say you start with this activation function, which in my mind are basically the the vector in the embedding space of a foundational model, stuff like that. And then you get you basically transform this vector into a longer vector of features that are interpretable. But I don't understand how those features are actually interpretable. I don't know if
Yeah, sorry, I forgot. Yeah, I mean, I went very quickly here. The point is that if what you would like are interpretable features, it means that you would like to, have, for example, a feature like here, a feature that activates every time you see the Golden Gate Bridge, okay? But the problem is that you do not observe this behavior here, because here the information is very, very compressed. It's in a very compressed format, okay? It's distributed. So basically, if you look at a single value among these 512, it won't be interpretable because all the 512 values will fire every time, basically. So you see the problem?
Yeah.
But instead, you translate it. So basically, you train a translation block here that projects to this absurdly high-dimensional space, which, I mean, I forgot to add it, but it's sparse, meaning that for every token here, only a few of these 131,000 features will activate. So here, maybe you are lucky, because if you look just a single element of this 131-dimensional space, maybe the single element in isolation is interpretable because it activates on interpretable stuff, you see?
So then you will pass, like, I don't know, the Golden Bridge word to your model and then look for the activation of the new features to see if they...
Yeah, basically for every one of these 131,000, you collect what tokens are maximally activating, basically what sentences, for example, are maximally activating. And then you try to see if they have a common interpretable explanation.
Okay, thank you. This is making more sense.
What I suggest, if you want to get better, to understand it better, there is if you go on Anthropic, they have a series of articles, let's say, where basically a lot of this came out. And for example, here, let's see if the one before the one that I showed to you. See, they have these features here, so many features. Sorry, it's impossible to. But you see, that's a little bit the point, that you start from an encoding that is very compressed and very distributed, and you translate it to an encoding that instead is very sparse. And because it's sparse, it's more interpretable.
I had a quick question. There's no more in the room. So you started off by drawing these diagrams of how scientists interacted with machine learning experts on their data. I wonder if you would change what that diagram looks like now and say how it might change in the not too distant future.
Yeah, I mean, what I saw is that right now it looks like this, in the sense that so many tasks can already be solved immediately, that you can throw up ChatGPT and ask all sorts of scientific questions. And in many cases, the answers are really good. I mean, you need a little bit of benchmarking to be sure, But it's actually incredible because, I have a lot of things we did in the past 10 years. I don't know, remote sensing, paleography. And if you try it out of the box with GPT-4, it's already really good at many of them. So you see, it's sort of the barrier is not existing. You just need a little bit, 20 euros or even a good GPU and DeepSeek, and you can already solve a lot of tasks. Of course, if you want instead to do this mechanistic interpretability, you need again expertise in these topics. I guess it will change again. So as soon as someone finds a very strong way of presenting these ideas in a good interface that works, people would be able to control the model with these interpretable features automatically with no barrier.
Cool. Thanks very much. Okay, I think we'll thank our speaker one last time then. So building on nicely from this, next month we have another talk from Mario Kren, who's research group leader of the Artificial Sciences Lab at the Max Planck Institute for the Science of Light. And he's going to be talking about generating kind of novel hypotheses in science using artificial intelligence, which dovetails very nicely with this talk. So thanks again. The recording will be online shortly.
Thank you. Bye.
Bye.